Hi, this script is the chapter 3 of the material testing. We are going to talking about the testing procedure of the material testing. In this chapter, the learning objective is to understand the testing procedure for material testing. It's going to include type of mechanical material testing, experiment design, specimen selection and preparation, and testing machine, instrument, and equipment. Let me talking about what we have for the first chapter. On the first chapter, we have a chance to talking about how to write a good report. The material testing report is a kind of technical report. So it's going to be in a given good format. And all the work you have done supposed to be neat, concise, and beautiful. And also the detail in the report supposed to tell about the behavior and the failure of the material, and also given some important value that's used in some specification. For example, if you do the tension test of the reinforcing steel, the results supposed to have the normal stress and normal strain, and the mechanical property you support to report in there is the modulus of elasticity, the yielding stress, the ultimate stress, and the percent elongation. Why? Because the specification and standard needs those four mechanical property to check whether the material is acceptable or not. Okay, and then we come to the chapter 2. On the chapter 2, we're talking about the data. After you do the testing in according to some specification, for example, the Thai Industrial Standard or the TIS. When you do the test, we're going to have a set of data, and then you got to find the mean of that data, which is called the sample mean. And you also need to find the SD or standard deviation. This standard deviation is important. If the value is large, that means the mechanical property of the material is no good. We like to have the SD with some specific value that's close enough to the mean. That means we also need to calculate the coefficient of variation, which is the standard deviation divided by the mean. And you can see from the table, the coefficient of variation of the mechanical property of the steel is about 5 to 10%, which is less than the concrete, which is about 10 to 15%. Why? Why the coefficient of variation of steel is set less than the concrete? Because the steel produced in a closed factory with some kind of good quality control, and the concrete is produced by using various material. So the concrete may have some more variable in the mechanical property. Okay, and then we come to the test. There is two types of testing. One, if you work in the manufacturing company, for example, in the Siam Yamato Steel Company of Siam Cement Group. In this company, you are working for the production, for the producer of the steel. So you're going to test a lot number of specimens to get the data to check the quality of your material is larger than what set in the standard. For example, if you test 100 of specimen and then you get the yielding stress of 300 megapascal, are you going to tell the buyer your material going to have 300 megapascal yielding stress? If you said that means half of your specimen going to pass for the mean, the 300 megapascal, and half will fail. So the reliability of using mean is not that high. And what you should do? By the chapter 2, it suggests that you're supposed to reduce the mean by some specific standard deviation. For example, if the standard deviation is 10, okay, if you use the mean minus by one standard deviation, you use 290 yielding stress. That means the reliability is going to be about 85%. And then if you use the mean minus 2 standard deviation, that means 300 minus 2 times 10, that is 280. The reliability will increase to 90 something percent. See, if you raise to mean minus 3 standard deviation, your reliability is going to be like a 99%. And then if you use the mean minus 4 standard deviation, that means 300 minus 40 is 260. That is going to be 99.99 something percent. That means if you like to be very reliable, you may need to use the mean minus 4 standard deviation to minus 5 standard deviation to make your product so reliable. Okay, that is the concept of making the mechanical property of material to be reliable. However, when you are the site engineer and then the producer sends the steel to you, you also have the duty to check whether that steel are acceptable or not. Usually, every 50 tons of steel, you may cut 3 to 2 meter bar, and then you send those specimens to the lab. If all of them, when you test, have the yielding stress past 250, you are going to be acceptable. If one of it is less than 250, for example, the one gets 260, another one gets 255, and the last one gets 240, you got to take 2 more samples from that steel to the lab, and the value of the yielding stress that obtained from the test must be larger than 250. That's going to be acceptable. If not, you're supposed to reject all the 50 tons steel back to the company. Okay, and now we come to the chapter 3. On the chapter 3, we are talking about how we going to set up the testing procedure, and we start by take a look at this steel building. This steel building, if you consider the purlin on the top of this steel building, by the theory of structure, you may see that the weight of the roof sheet and the weight of the beam, that's going to be the dead load, and the life load from the wind or the rain is going to transfer to the purlin, and the force that's transferred along the purlin may be uniformly distributed load. Okay, when you analyze this beam, if you set it up as the simple support beam, you can find the reaction. Then you can draw the shear diagram and the moment diagram, and you take the maximum shear and you take the maximum moment to design the section of the purlin. That is the theory behind the analysis of the purlin. And then you should check the deflection of this purlin. And when you check the deflection of this purlin subjected to the uniformly distributed load, and it is the simple beam, you can go back to Mechanics of Material chapter 12 and you can open the deflection table. The maximum deflection that occur on the beam with uniformly distributed load gonna occur at the middle part of the beam, and it's going to be Vmax equal to 5 times W, the size of the loading, and times L, the length, power flow, divided by 384 times modulus of elasticity and the moment of inertia. W, you calculate, for example, 10 kilonewton per meter, and this length may be 4 meter. And then if you get the section when you design this beam, you know the I. So the equation, you need to know the E. So what is the E? The E is modulus of elasticity of this steel material. You can obtain the E only by testing the steel. So the theory and the material testing result are both important because they are going to put the result into the equation to get the value from the theory. If not, you got to do the real world testing. You got to put the load into the beam to measure the deflection that is acceptable or not. That's going to cost you a lot of money. So sometimes we use the theory to predict what happened in the structure. However, at that time you got to have the material testing result to get the required value. So that is the two things about the theory and material testing. It's like you have a coin. It have the front and the back. It's going to get together, okay? And what's next is the example. This is the beam that I mentioned. Is supported by simply supported beam. It have the pin and have the roller, and what? And it has under the force the Vmax, and then by the structural member, and then you use the double integration, and then you will receive the deflection equation that I mentioned. W is 10 kilonewton per meter, L is 4 meter, I you get from the design, and E you must test this. This is the detail of what I've said. In the design procedure also, we do the shear diagram and moment diagram, and then we get the Vmax, and then we have the Mmax. We use the Mmax to find the fractional stress. The fractional stress must equal to the allowable stress. The maximal stress comes from the theory. The Mmax comes from the theory. However, the allowable stress does come from the test. Most of the time, the allowable stress is the yielding stress for the steel divided by factor of safety of 2. Okay, and then if you do the calculation by this, and your beam have the rectangular section with the width of B and with the depth of 2B. So the moment of inertia can be calculated with B width times depth cube power 12, and then you got it for 2B power 4 divided by 3. You plug this into this equation, and from the test you got the allowable stress of 100 million Newton per square meter, and then you got the maximum moment of 10,000 Newton meter. You put them in the calculator. You got the width of the beam that can resist the maximum moment. Okay, that means what? That means you do the test, right? And then you check for the Vmax. Okay, the section, the obtained section must has the tau max that's less than the tau allowable. Again, tau allowable is come from the test. If not, you got to redesign the beam and get the larger section. And finally, as I mentioned on the first slide, that we got to find the Vmax, and it's up to your type of beam. You can select from the diffraction table and you can determine the maximum moment. The maximum diffraction. The maximum diffraction must less than the allowable value given by the design code. For the beam without the wall under it, that is going to be the span divided by 240. If the beam has the wall, the brick wall under it, the allowable diffraction going to be less. It's going to be the span divided by 360. You may go to chapter 12 of mechanics of material to check this one out. Okay, next, let us go to the mechanical property that we should understand what the meaning of it. Okay, and the first one, we're talking about the strength. When we're talking about strength, the concrete have their own strength. The steel also have their own strength. How do we get the strength of a material? Okay, first, what is the definition of strength? The strength is the ability of material to resist the applied force without failure. So that means the strength is depend on what we define the failure. In the steel, we define the yielding as the failure of the material, because after yielding, the material will deform a lot, so much that the structure cannot perform its intended function. However, for the concrete, when we test the concrete in compression, we got the stress strain diagram. And then the stress strain diagram will have the maximum ultimate stress. The maximum ultimate stress of the concrete occurs when the strain equal to about 0.002 to 0.003, and that very close to the yielding of the steel. So for the concrete, they use the ultimate compressive stress, and for the yielding, for the steel, they use the yielding, and both of the yielding and the ultimate stress occur at the strain about 0.002 to 0.003. Okay, by doing that, we will set the steel at the yielding and the ultimate at the compressive stress. Okay, next, the stiffness. The stiffness is important because the material with high stiffness will deform less than the material with less stiffness, such as rubber. Rubber have very small stiffness compared to the steel. And what is the stiffness? The definition of stiffness is the ability of the material to resist the deformation under the applied force. Usually, again, from the stress strain diagram that we use from the strength, we measure the slope when the steel is linear, when the concrete is linear. If you measure that, you will get the modulus of elasticity of the steel of 200 gigapascal. And you get the modulus of elasticity of the concrete is about 20 megapascal. That means the steel is 10 times more stiff than the concrete. Okay, and next we talk about the elasticity. Elasticity, you think about the rubber band. The rubber band can elongate significantly under the force, and then when you release the force, it come back to the given length. So the definition of elasticity is the ability of the material, such as rubber band, to be deformed under the applied force without permanent deformation. Without permanent deformation. Okay, and it's also checked by the stress strain diagram. For the plasticity, you're thinking about the steel. The curve of steel in first portion until the yielding is have the strain of 0.002. That is the elasticity of the steel. However, after steel go to the yielding region, go to the strain hardening region, and go to the necking region, and steel will fail at the strain up to 0.3 or about 30% of its original length. So that means the steel have very large plasticity. For example of that, we can say the definition of plasticity is the ability of the material to be deformed permanently under the applied force without fracture and rupture. So for the stress strain diagram, if you recall, we separate into the first part elasticity and the second part as the plasticity. Okay, and the last one is the energy capacity of the material. Thinking about when you select a material to build the guardrail of the bridge on elevated highway, that is maybe 20 or 30 meters above the ground. And if your material built by the material such as wood, and then your car crash into the wood rail, what happened? The wood will break easily, and your car can drop down to the ground, and people in the car may die. However, if you change to the material such as the steel, when the car hits steel, steel can absorb a lot of energy from the car, and sometimes it can rebound back, putting the car on the road. That means when the steel absorbs the energy of the car and hold it, they use the plasticity to taking care of the energy that is absorbed. By this example, that means the material that can have large plasticity can absorb more energy. So the definition of energy capacity is the ability of material to absorb the energy during the applied force. And we have two types of energy capacity. One is the modulus of resilience, okay, and another one is the modulus of rupture. You may go to chapter 3 of the mechanics of material. You can see that. Okay, next, let's us use this stress strain diagram and try to understand what the definition of strength, stiffness, elasticity, plasticity, or even the energy capacity. On this stress strain diagram, there is two parts. One, the result from the tension test, and another result from the compression test. Let me say, some of the material are good in compression, such as the concrete. Most of the concretes have good compression mechanical property, because concrete is produced by mixing the Portland cement with the water, with the sand and the crushed stone. So when mixing this concrete has the air void in it and have some crack in it during the process of hardening. If you pull the concrete, that's crack, that's air void going to grow very quick, and then the concrete cake can take only less tensile stress. However, when you compress the concrete can take a lot of force because the compress the crack stick together, so it can take a lot of force, okay, and the cast iron also. However, the steel can take most of the tensile and compression in the same manner, and testing the steel or aluminum or cast iron in tension are more easier than testing in compression. So in many cases we use the tension test to determine the mechanical property of various materials. What various material we have here? One is rubber. Rubber have linear elastic like this. Another one is wood and cast iron and aluminum alloy and the low carbon steel. When you see the stress strain diagram and then you take a look at it, what is strength of each material? You can see that the strength of material can be defined by the yielding stress of the low carbon steel. That is going to be about 250 or 260 megapascal. This material have the yielding portion clearly, so you can find the yielding easily. However, the aluminum. For the aluminum, we cannot find the yielding region of this aluminum, so we got to use the 0.2% offset. 0.2% is 0.002. That is about this, okay, and then you draw the line parallel to this graph and then cut it about here. So the aluminum may have the yielding stress of 220. That's a little bit lower than the carbon steel. And cast iron also has cast iron has no yielding stress. So cast iron has to be very similar to aluminum. So this cast iron usually we define the yielding the same as the proportional limit of the material and the same as the wood, okay, and by doing that you can see that the highest strength material is going to be the low carbon, and then the aluminum alloy and the cast iron and the wood and the rubber. And then the next, talking about the stiffness. Which material is the most stiff material from this graph? The material that has high slope in the linear elastic behavior. So the rubber going to be smallest stiffness, and the wood is better. The cast iron is larger, and aluminum is also larger than the cast iron, and the most stiffest is the low carbon steel. And next, comparing the elasticity. The elasticity of the low carbon steel is occur at its yielding point. Okay, it's about this. The aluminum alloy have the yielding point about here, and then you can project down here. And the cast iron is going to have about this. The wood about this, and the rubber about this. So if we see the first part of the graph, we can see that the rubber has the largest elasticity, and then the low carbon steel has the smallest elasticity. Okay, next we compare the plasticity. The low carbon steel has the very small elasticity. However, the low carbon steel have very large portion of the curve. in the plastic steel region. So for the plastic, the low carbon steel have quite larger plasticity compared to aluminum, compared to cast iron, compared to the wood. And the last one, the energy capacity. For the energy capacity, you compute the area under the stress strain diagram. If you compute for the rubber, this is going to be the total energy capacity of the rubber. However, if you see the low carbon steel, the area under this stress strain curve is very large. So the low carbon steel going to have very large energy capacity compared to the cast iron, compared to the wood, compared to the rubber. Okay, that is the example that we compare based on some important mechanical property that we mentioned before. And there are some questions. Which material, for some more important question, which material is a ductile material? Which material is the brittle material? Okay, go back. What I'm talking about the concrete. The concrete can take very small tension. So the concrete in tension is the very brittle material. However, the concrete in compression can deform about 0.002 to 0.03, which is close to the yielding of the steel. So the concrete in compression is more ductile than the concrete in tension. So the same material is depend on you test the material when you classify which material is ductile or brittle. So you got to ask, you're going to classify is based on the tension or based on the compression. Okay. Anyway, the ductile material is supposed to deform a lot. That means the low carbon is the ductile, the aluminum is the ductile, the rubber is the ductile, and the cast iron is the brittle material. Which material is proper to be used in tension member? Okay, for sure, the aluminum, the cast iron are good to be used in in tension member. Which material are appropriate to use in compression? For sure, this is concrete and the cast iron. The cast iron have very high strength, for example 280 compare about only 140 in tension. And which material is the stiffest one? That I mentioned about it already. Recall it. Do you remember what I'm saying? Okay, it's a low carbon steel, right? Okay, and then we go to the types of mechanical material testing. In the types of mechanical material testing, we can separate by the loading method and the testing condition. For the loading method, we consider how to apply the forces to the testing material. And you may recall from this picture, and then we have the strong beam on the top of it. We have the loading cell here, and then we have the support for the beam here. When this lower part moving up, you can see that this beam gonna defect like this. So the force that's applied to this test is going to produce the fractional stress into the specimen. This is the way we test the beam, right? However, if we have the steel specimen and then we put it in tension, so the stress in the tension is going to be the normal stress in tension. And in compression, you also put the compression into the specimen, and then it's produced the compressive stress and the other. Okay, from this one, we can model the test over here into this picture. The force from the machine that can measure for this blue cell is the P, and then the deflection of the beam can measure from the lift up of the bottom. And then from this graph you may plot the P and Vmax relationship, in which we are going to test in this form in the laboratory for the testing of the steel, for the cast iron, for the wood parallel to the beam. Okay, and what I like you to do is, how can you find the Mmax? You need to go back to static. You got to draw the free body diagram, and then you can use the equation of the equilibrium to find the reaction. And then if you not draw the shear diagram and moment diagram, you may cut the beam to determine the Mmax, and the sigma max is going to be here, and Vmax is going to be in this equation. And again, go back to the first part of our discussion. You can see that the equation cannot be used if we don't know the modulus of elasticity of the beam. Anyway, I like to assign you guys to go back to try to draw the shear diagram, moment diagram, and also the elastic curve of this beam. And I like you guys to derive the equation for the deflection of this beam also, to get more in depth or to review your mechanical property, which is the basis for the marine testing. Okay, for the loading, as I mentioned before, we have many types of loading. The picture before is produce the fractional stress, so that's called the fractional test. For this picture, the specimen is in tension. The stress inside is going to be normal tensile stress, so this is the tension test. For the concrete going to be compresses. The stress inside the concrete is compressive normal stress. Okay, we call this is compression test. And for this machine, we put the specimen between this, and then we rotate this. The specimen twists, and when specimen twists by the torsion T, we are going to determine the shear stress tau equal to T R. T is torsion, time R is radius, divided J, the polar moment of inertia. So this one we call is torsion test. And the last one, we mentioned about this before. Again, for each test, I would like to assign you guys to draw the free body diagram of each test by using your static and mechanics of material knowledge. When you do the tension test, for example, you're going to find some mechanical property of material that's compared to what's specified in the standard and specification. For the tension test, you may get a lot of mechanical property, but there are only 4 of them are important. The first is the yielding stress. The second is ultimate stress. The third is modulus of elasticity. This one, and this one you can determine from the stress diagram. So you got to determine, you got to draw the stress strain diagram of the material to get these 3 properties. And then you got to find the percent of elongation. This one shows the ductility of the steel. Most of the time, the standard and specification give the percent of elongation of the steel larger than 20%. And for the compression, only 2 mechanical properties are interested. One is the ultimate compressive stress. This is the strength. Okay, and another one is the modulus of elasticity. That is the stiffness of the concrete. For the fractional stress, you determine the strength, fractional stress as the yielding point. The first one is the strength, and also the last one is the stiffness. You determine the second fractional modulus of elasticity. In this method testing, you guys will determine those important mechanical properties for each test, for the tension test, for the compression test, and for the fractional test, for example. And next, when we consider the testing, we also to consider the rate of loading to the specimen. Most of the tests that we have, the tension test from lab 2, the torsion test from lab 3, or fractional test or compression test, most of the time the test is considered static test because the tests were performed with the load that's very slow. Okay, that is very important to our engineering application. However, for some engineering such as the aerospace engineering, the automotive engineering, they also do the dynamic tests because the material used in car and in aerospace vehicle is going to subject to maybe the heat from the bird, and the load is going to be the dynamic. So they got to test something like this. In this test, the specimen is set over here, and then you have the weight here, and when you release the weight, this one going to swing and hit to the specimen and measure how it's going to behave under the heat of the weight. Okay, and the last one is a little bit also important for our civil engineering application because it's also occur in the concrete. For the long-term tests, such as the creep test of concrete, is important because concrete is the composite material. It's manufactured by mix the Portland cement with the water and with the sand and the cut stone, and it has some air wall inside it. When the concrete is subject to long-term load applied on it, the water that is in the air void will move out of the concrete, and then the concrete gonna have some permanent deformation for the long-term application of the force. So this creep is important when you do the design of the pre-stressed concrete structural member such as the beam or the column. And also we consider the number of loading on the specimen. Most of our tension tests, compression tests, torsional tests, shear tests are the one cycle testing. However, we have the fatigue test. In the fatigue test, the specimen rotates, and the stress on the specimen will change with the rotation of the specimen. So when the specimen, which have very small micro crack, have the tension, compression, the crack going to be open, close, open, close, open, close. When it's repeated for many times, the material will fail by fatigue of the material by itself. So this is important when we design the beam that's subjected to the moving vehicle. So the frame will deflect every time the truck pass the bridge, pass the beam of the steel bridge. Okay, and we also have this kind of testing, but it's going to be tested on the aluminum. Okay, for the testing condition is the next topic we should talk. You may see our engineering structure may be in different kind of looming or temperature. Some of them may be in room temperature, some of them may be low temperature, some of them in going to be in high temperature. The steel, for example, is very special. At the room temperature, the steel may be have at the ductile material. However, if you use that steel in the very cold building or in very cold regions such as near the North Pole or near the South Pole, the steel may change to the brittle material. So you got to consider that brittleness when you design the steel in the very cold environment. And the test of the steel also is going to test in very low temperature. In the opposite, if you use the steel in high temperature area, the steel going to be softer and also have some kind of creep behavior. For example, if you use the steel in the cement production factory, that is going to have very high temperature there. So you got to consider that's going to affect, and then you got to test the steel with that high temperature, with that low temperature. Okay, next, talking about the moisture. The moisture have the bad effect on the steel. Even the steel put it in the concrete. The concrete can protect steel for somehow, but not the total. Because when the water come to reach the steel will react with the water and get rusted. When it get rusted, the steel will spoil out, the concrete out like this. And then the steel reinforcement gonna deteriorate very quick. And when the steel deteriorate too much, this kind of structure may fail. So in the ocean, in the shoreline structure, you got to consider this very in detail. And also for some chemical agent such as the one in the treatment plant, you also need to use special concrete with some specific additive to make the concrete very durable for the chemical agents. Okay, for the external design. For the external design, you got to consider the standard. And we have two symbols over here. This one for Thai industrial standard. This one for American Society for Testing and Maintenance standard. Okay, when you design the experiment, that is important to follow this. And then you got to answer some question. What is the importance of the test and the importance of the structure for the test? For example, if you are an engineer who is working to build the airplane, and also if you are an engineer, you are responsible for building to build this transmission pole. We say the airplane supposed to be light, to move fast and use less fuel. So the factor of safety for the airplane is going to be only 1.2 and 1.3. So the test result for the airplane must be reliable, must be very high accuracy and precision. So most of the tests of aluminum, the composite material, or the steel used the airplane, they are going to be very detailed with high reliability, with high accuracy and precision, and the cost of tests are going to be higher. But for the steel that's using for the transmission or radio transmission pole, that maybe have very high factor of safety. So the test of this may be less reliable due to the higher factor of safety and less accuracy and less precision also. So the expense used in this test of the steel may less than the one used in the airplane industry. That is very important thing we supposed to think. Next, let's imagine we like to build the roof to cover, for example, the parking lot. Okay, let this picture represent our parking structure, and we like to build the steel truss, the same one in the theory of structure. And if you like to build this truss, you need to answer the following question. So what are the mechanical properties of the steel you use in the design? Okay, when you are a truss, you know some member are going to get the highest tensile stress, and also some member are going to get the highest compression stress. When you decide the tensile stress, you got to know the yielding stress. When you divide the yielding stress with factor of safety, you got the allowable stress, and then you get the size of the structural member. And then you also check the deflection of the truss. So you got to know the modulus of elasticity of the steel to represent the stiffness of the truss. And one more thing that you need to know is ultimate stress, because ultimate stress will show you a more safety that the truss can take. Okay, and second, if you like to know the modulus of elasticity and you like to know the yielding stress, what kind of tests you should perform? That means you got to do the tension test mostly because it is the steel. When field, you may use the compression test, but most of the time we use the tension test. How the test results are related to the use of the steel in this roof truss in the design. As I mentioned before, the yielding stress gonna divided by factor of safety to be the allowable stress, and also the deflection of the truss. You're going to use the modulus of elasticity to put into the equation we have used to predict this truss deflection without you need to do the full scale test, which is very important. And what are the limitations of the test in question T? It's up to what machine we are going to use. And let's consider these two machines. You may see this machine going to provide more accuracy, okay, in the test more than this one. And you will see in the lab that this one will produce some error from your test from your lab number 3. This one will produce very high accuracy from the lab result of number 3 also. And the cost of these two devices are different. This is like a 5 million baht machine. This is going to be like a 200,000 baht machine. So the cost of the machine also the important factor. And if you have this one, you just use this one because it's going to provide you a better result. And then what level of accuracy, precision, and reliability of the test result? That's going to be up to the standard you use, because the standard provide all of this that you must follow. What kind of testing specimen should be used in the test? It's up to what kind of steel you use. If you use the steel with the structural section, okay, you may cut part of that structural section to be the rectangular and put it into the machine. And for the example like this, usually we didn't do much, okay, and sometimes we also use it. It's up to the standard that's we to use. And the last one, how many testing specimens should be used? If you're testing for the construction for acceptance of the material that producer send the material to you. You may check it's by 3 or 5. If you are the producer of the steel, you may test it for 100. Okay, next. Specimen selection and preparation. Again, we need to go back to the standard what we have, the TIS or the ASTM or the JIS, even for the British standard BS. You got to follow that. You got to take the specimen with some specific size and shape and with allowable less than the allowable error. The number of specimens must be enough. Like most of the concrete cylinder, actually we test them only 3. But when we collect the specimen, we collect for 5. Why? Because if one of that concrete cylinder won't pass the test, we can take the rest of them to represent the concrete we are checking. Okay. And then 3.5, the testing machine, instrument, and equipment. In the selection of testing machine, instrument, and equipment, we need to consider the objective of material testing. As I mentioned, if you test the material for building the airplane, and you're testing the material to build a parking garage, these two have different objectives. Because for the airplane, you got to have higher accuracy, higher precision, and higher reliability due to the factor of safety of the analysis and design of the plane is very small to make the airplane as light as possible and can take all the expected load. So the fuel consumption of the airplane gonna be low. But for the building, in some time we build the building with the one that has large element to make it more durable. That means it's up to what we set as the objective, which reflect to the level of accuracy, precision, and reliability. And if you have very detailed testing, for sure the cost of testing is going to be more expensive. So in the measurement that we have in the lab, number 1, you may watch my video clip that I show you. We do the tension test. When we do tension test, we measure what? We measure the force, and also we measure the length. Or in the second week, we also have a chance to test the concrete in compression. So you measure the compression force. You also measure the contraction of the concrete. So most important of civil engineering are the length and applied force. And when you measure it, there are some error that we got to know it. Okay, if you have 4 people in your group, and then Ajahn give you a tensile specimen and ask every one of you to measure the diameter of the specimen. You know what? What you measure, what each of you measure, they are not the same. For example, some may measure to get 5.1 millimeter. Another one may get 5.12 millimeter. Another one may get 5.14 millimeter. And another one may get 5.08 millimeter. This kind of error is called a random error. It occurs randomly. The random error is a kind of accidental error. You can correct this by compute the mean and then compute the standard deviation. If standard deviation you obtain is low, your testing is acceptable. You may use the mean and represent all of your measured diameter. It's going to be 5.08 plus 5.10 plus 5.12 plus 5.14 and divide by 4. Another one is a systematic error. That error going to be systematic. It means the value going to be on the left, on the larger side or the smaller side of the accurate one. If you have your 10-wheel truck, okay, most of the 10-wheel truck going to have the velocity meter that is kind of getting the value lower than it actually is. That's maybe because when you put the tire into this 10-wheeler and the tire is too big, so the speed going to be larger than it should be. Okay, this is example. If you drive your car with 100 km per hour and the speedometer set is 99 km per hour, then if you drive it to 110, you may expect your speed gonna be like 108.9 km per hour. How do you get this? You just use the proportion. The 100 get 99, 110 going to be 110 times 99 divided by 100, so you get 108.9. So the systematic error can be correct easier by proportioning the value of what you like to have. And the accidental error, like I said, is the random. You got to use the statistical analysis to adjust the value of measurement. Okay, that is the end of chapter 3, and I hope you guys enjoyed it. And if you cannot catch what I'm explaining, you're supposed to review or try to study your material with this lecture again and again. Okay, that's it. Bye bye. End of chapter 3.